Good morning viewers. Today we'll have a discussion on the introduction of analytical instrumentation. In today's discourse we'll cover the following topics: introduction, analytical instrumentation block diagram, steps involved in analytical instrumentation procedure, selecting an analytical method, understanding the measurement process, use of microcomputer in analytical instrumentation, and finally the classification of analytical instruments. Analytical instrumentation is a study of the quality, separation, identification, and quantification of the chemical components of natural and artificial materials in a given sample. Molecules possess three types of internal energy: electronic, vibrational, and rotational. Electronic transitions correspond to the ultraviolet and visible region, vibrational transitions to the near infrared and infrared region, rotational transitions to the infrared, far infrared, or even in the microwave region. When a beam of radiant energy strikes a surface, the radiation interacts with the atoms and molecules of the substance and undergo any of the following properties: absorption, transmission, scattering, deflection, reflection, and refraction. Analytical instruments provide information on the composition of a sample or matter. The instrument comprises four basic blocks: chemical information source, transducer, signal conditioner, display system. The simplistic block diagram representation of an analytical instrumentation is shown below, where the sample is first injected with a stimulus. The changes in the sample are studied by the transducer, and then the signal processor conditions the signal. The readout meter is the final display unit where we analyze the output. The first two elements constitute the characteristic module, whereas the last two constitute the processing module. Any analytical procedure comprises the following steps. First, we define the problem. Then we select the appropriate method for the particular problem. Obtain and store the sample and then pre-treat the sample. After preparing the sample, we perform the required measurements, compare the results with already present standards, then apply necessary statistical methods, present the results in forms understandable to the analyst, and finally present the result to the customer. So in brief, define the problem, detect the method, physical and chemical properties are analyzed, amount of sample required, we check for the availability, we also check for the concentration range of the analyte, and then finally come to the conclusion. Selection of the right analytical method guarantees the best analysis. The following factors are taken into consideration while selecting an analytical method: accuracy, precision, sensitivity, specificity and selectivity, robustness and ruggedness, scale of operation, equipment, time and cost, and then finally making choice based on the above 7 parameters. The other factors that you keep in mind while selecting an analytical method are speed of the equipment, ease and convenience of the equipment, the skill set of the operator, cost and availability of the equipment and samples, and per sample cost. All analytical procedures can be in any of the following domains. There are three domains: analog domain, digital domain, and time domain. In the analog domain, information is encoded as the magnitude of current, voltage, charge, or power. Information encoded is continuous in amplitude and time. Amplitude is related to property of interest. In the digital domain, information is encoded in the form of a number, generally binary encoded. Output is displayed as logic labels of high or low. Fundamental unit of information in digital domain is bit, that is either a 0 or a 1. In the time domain analysis, information is encoded in the form of a time-dependent fluctuation of a signal. Frequency of fluctuation is related to the property of interest. That is, in photon counting, the rate of arrival of photon at the detector is related to the intensity. So to summarize, while selecting an analytical method, these particular numerical criteria are to be maintained: precision, bias, sensitivity, detection limit, dynamic range, and selectivity. The statistical parameters which found immense importance in analytical methods are absolute standard deviation, relative standard deviation, standard error of the mean, coefficient of variation, and variance. The table given below shows the characteristic property and the instrument required for conducting analysis based on the characteristic property. Emission of radiation, we use emission spectroscopy and fluorescence, phosphorescence and luminescence. For absorption of radiation, we use spectrophotometry and photometry. For scattering of radiation, we use turbidimetry, nephelometry, and Raman spectroscopy. Refraction of radiation, we use refractometry and interferometry. For diffraction of radiation, we use X-ray and electron diffraction methods. Rotation of radiation, we use polarimetry, optical rotary dispersion, and circular dichromism. Electrical potential, we use potentiometry and chronopotentiometry. Electrical charge, we use colorimetry. Electrical current, we use amperometry and polarography. Electrical resistance, we use conductometry. For mass, we use gravimetry. Mass to charge ratio, we use mass spectrometry. Rate of reaction, we use kinetic methods. For thermal characteristics, we use thermal, gravimetry, and titrimetry. Differential scanning, calorimetry, differential thermal analysis, thermal conductimetry methods. And for radioactivity, we use activation and isotope dilution methods. Here we see the most commonly used analytical equipment and how they respond to different criteria. For photometer, the energy source is tungsten lamp. The analytical information is attenuated light beam. Information sorter is filtered. Input transducer is photodiode. Data domain of transduced information is electrical current. Similarly, for atomic emission spectrometer, inductively coupled plasma is energy source. Ultraviolet or visible radiation is the analytical information. Monochromator is information sorter. Input transducer is the photomultiplier tube. And the data domain is electrical current. For colorimeter, DC source is the energy source. Charge required to reduce or oxidize the analyte is the analytical information. Cell potential is the information sorter. Input transducer are electrodes, and the data domain is time. pH meter uses sample glass electrode as energy source. Hydrogen ion activity is the information. For analysis, glass electrode is the information sorter. Glass calomel electrode is the input transducer. Electrical voltage is the data domain of transduced information. Mass spectrometry, the energy source is ion source. Mass to charge ratio is the analytical information. Mass analyzer is the information sorter. Electron multiplier is the input transducer. Electrical current is the data domain of transduced information. For gas chromatography with flame ionization, flame is the energy source. Ion concentration versus time is the analytical information. Information sorter is chromatographic column. The input transducer is biased electrode, and the data domain of transduced information is electric current. The example of pH analysis, we understand the measurement process of analytical methods. First, we take the signal generator glass electrode, then we transduce the signal, information encoded, different in pH to potential difference. Then we modify the signal, information decoding, voltage to pH, and finally we have the signal display. Information encoded, processed, transferred, and decoded and displayed, and steps in the measurements involve transformation and processing of the signal between different data domains. Microcomputers find tremendous application in analytical processes for the following reasons: control of the instrument, processing data, storing data, displaying data, and transferring data. The figure below represents an exhaustive classification of all analytical instruments. The analytical instruments can be broadly classified into three categories: biological method, chemical method, and physical method. The chemical methods are called the classical methods, and the physical methods are called instrumental methods. The biological methods are further categorized as in vitro animal studies and microbiological. The chemical methods are again further categorized as gravimetric and volumetric. The volumetric are divided into acid-base titration, redox titration, precipitation titration, and complex metric titration. The physical methods are broadly categorized into 5 subsets: optical spectral method, electrochemical method, miscellaneous method, chromatography, and hyphenated techniques. Under the optical spectral method, we have 4 major types of devices: EPR, absorption, ultraviolet, IR, NMR spectroscopy. EMR, emission, fluorescence, phosphorescence, flame photometry, scattering or refraction, nephelometry, turbidometry, Raman scattering and refractometry, and rotation of EMR and polarimetry. The two other methods are mass spectrometry and colorimetry. Under electrochemical method, we have pH metry, potentiometry, conductometry, voltammetry, polarography, amperometry, and colorimetry. Under miscellaneous methods, we have thermometric analysis, thermogravimetric analysis, DSC, RIA, ELISA, flame photometry, elemental analysis, Kilzer method, and autoradiography. Under chromography, we have planar chromatography and column chromatography. The planar chromatography can further be of paper type, thin layer chromatography, and high performance TLC. The column chromatography can be column gravity, gas, flash, HPLC, size exclusion, ion exchange, affinity, UPLC, and droplet counter current. The hyphenated techniques are merger of two methods into one method, which can be of GCMS type, LCMS, LCNMR, GCNMR, GCMSMS, ICP, OES, ICP-AS, ICP, and MS. So this picture depicts all the major classifications of analytical instruments. For further reading, the students may refer to the following links